Hello guys, welcome to DS from scratch. In this video, I will show you a project on time series forecasting. So this project is, as I said, on a time series forecasting of water quality data using LSTM and attention mechanism. This data set is hourly water quality data from Burnett River of Australia, which has been downloaded from the link provided in the notebook. You can use this link also. This link you can use for getting the data set. So here we can have a look to the data. The first five row of the data. So it contains uh, seven different important water quality variables of the river. The data have been collected half hourly from the digital stations, but then we have converted to hourly data by taking the average of two values in each hour. So let's have a look to the statistical characteristics of the dataset. Here we have 39,958 samples of each variable, which corresponds to 39,958 hours, which is 5 years from January 2015 to last December 2019. Then we have the mean of each variable, standard deviation, minimum 25 percentile, 50 percentile, 75 percentile, and then the maximum of the values. So here I have checked that if there is any non-value available in the dataset. As you can see that there is no non-value in our dataset, but it is not the only case that will cause problem. Outliers is another problem that can cause uh, some problem or some inaccuracy in our model. If you can see that I have used box plot to visualize the outliers in each variable. As you can see that in case of chlorophyll, we have this much outliers. In case of dissolved oxygen, here this much outliers for upper limit, and this much outliers less than the lower limit of the dataset. So all the variables except the temperature, as you can see, the temperature has no outliers. Except this, all other outliers or having all other variables are having outliers. Very, as you can see, that turbidity has very huge number of outliers, and also the pH. So dealing with these outliers is our priority before using this data into our model. So I am using quartile. In quartile, first I am finding the first quartile using the percentile function, which is the 25th percentile. Then the third percentile, which is the 75th percentile. Then enter quartile, which is the third quartile minus the first quartile. Then after having this, we can specify the lower limit and the upper limit using this function. Okay, our upper limit is uh, q3 plus 1.5 interquartile, and lower limit is q1 minus 1.5 interquartile. Okay, so here we can say that if the in our data dt, which is our data, if the dt any value greater than upper, or any value in this dataset less than the lower, just put it as non-value. Okay, so after putting this non-value, then we will decide what to do with those non-values. First we will declare the outliers as non-values, then we will decide. So as you can see that after running this for loop, we can see that for chlorophyll we have 909 non-values which corresponds to the outliers. For DOMG, we have 876. Similar to that, for all other variables, we are having outliers except temperature. For temperature, we don't have any outliers, so we don't need to fill those values. Okay, you can see here it is a representation of the data set. Again, you can see that here we none values exist. Okay, so our purpose is to fill these none values. So there is a function in pandas binomial of interpolate. Using this function we can use different methods, linear or polynomial or any other method for filling the non-value. So we are using this function, very easy function. Just say data dot interpolate method linear axis 0. Which axis? Like if it is filling the data, so which axis should it use for interpolation? If you are saying 1, it will use like this, like if here is none, it will use this values. It will take the interpolate of these values and then it will fill this none value. If you are saying none, then it will use these values. Okay, these values in its columns. So make sure that which axis you want to use for your interpolation. Axis 0 means column wise it will interpret. Axis 1 means row wise it will do interpret. Okay, so after interpolating, we can see that there is no non-values uh, showing, non-values available. It means we filled all the non-values. So after that, let's have a look again that if there is any outlier still exists. As you can see that there is no outliers. So we have get rid of those all outliers. Now we are ready to go on with our method. So here is a visualization of the data, time series data. In the x-axis, you can see we have time in hours, and in the y-axis we have dissolved oxygen in milligram. Okay, so this is a time series plot for all the data from hour 0 to hour 40,000. So for our convenient, we can convert the data from uh, data frame to array. So this is you can see in array format. So further we can use this for our process. So before feeding this data into the model, we have to do some pre-processing of the data, which is normalization. We are using min max scaling from scalar preprocessing function. Scalar we have declared as min max, so it will scale the data in a range of 0 to 1 using the maximum and minimum of the data. So its function is like x data minus min. Okay, minus min over x max minus x min. So this is also x min. Okay, so x, any value of x minus x min over x max minus x min, it will directly give you the range of values between 0 and 1. So we want to have all our data into the range of 0 to 1. That is why we are doing normalization. For LSTM, it is like very important to normalize the data set and then feed it into the model. So we are, as I said, we are using a min max scalar from scalar. Here you can see. Then I have used a for loop here, which I'm uh, scaling each column separately. So I'm using only the mean and max value of the same column for that variable to scale the data. Okay, so this is for min max scaling. And One important thing for LSTM is phase space reconstruction of the data. What do we mean by phase space reconstruction of the data? It means that if you have if you have a data of x1, suppose x2, x3, and your data goes up to xn, and you have n number of samples. So what you will do, you will phase space reconstruct. Phase space reconstruct means, like, for predicting our next value, how many values should the model look back. Okay, so if we put a time window of 2, okay, it will take x1 and x2 as input to predict x3, and it will take x2 and x3 to predict x4, and it will give similarly to that x3, x4 to predict x5. Similar to that, if we have xn, it will take xn minus 1 and xn to predict xn plus 1. So this is what we mean by phase space reconstruction, okay, or to create the data set for LSTM. Here I have written that function to get the values for as input, and then I have put I have declared the function for getting the labels or the target value from our data set. Okay, so let's look at into the function. In the function, we have declared the function as create data set. It will take data, then time window, then level. Okay, time window means the number of time steps you want the model to look back. I mean, like, if you want to predict for tomorrow, how many values, how many days should the model look back for predicting that value. And the label means, like, you have different columns, okay, in your data set, different columns. Which column should it take? Column 1, column 2, or column 3? Okay, so this we mean by the label. Okay, so we will save the data into x and y. Here I have said x and y. X and y is an empty list. Then for I, in range of length of data minus time window minus 1. So it will go up to, like, if your time window is 2 and your data is 10, it will go up to 7th value. Okay, up to 7th value. Then from 0 to 7 it will take. Okay, so then it will take data from I up to I plus time window and all the columns. Okay, so if you want to get one dimensional data, then you have to prepare your data accordingly. Okay, but this function gets all the dimensions in your data set. Then coming to the target value y, we can say y dot append data I plus time window label. Okay, I plus time window means, like, if your time window is 2, it will take it is 0 plus 2, it will take that third value x1, x2, then x3 will be the label. Okay, then it will append to y. So this is for creating the data set or reconstructing the data set. Then we use this function for splitting the data into train and test. I'm not using any predefined function. I have just said that data array from 0 up to 75 percentile, 75% of the percentage of the length of the data take as training data, and then up from 75 up to last value take it as test data set. Okay, so that is how you split the data into train and testing, but you can also use the scalar predefined function for splitting the data into train and test. Then after that we will be using that create data set for reconstructing the data into train and test. As you can see, it is x train, y train, create data set. D train is our data set, then 100 is our time window. We want to look back 100 hours back as our data is hourly. Then the label should be 1. Label 1 means the second column will be our target value. Okay, so this is for creating the data. As you can see here, the shape, the output of that function will be the for our input will be a three-dimensional array. Okay, the first dimension is the number of samples, the second dimension is the number of time window, and the third dimension is the number of the variables. So we are having 29,867 samples, 100 time steps, and 7 different variables. So for y it will be only one dimensional data set with the same number of samples as we had in input. Okay, so after doing all this pre-processing, we can now define the model. We are using sequential model from the keras, then we are importing LSTM and dense. So we can say that model initiate with sequential, then after that add one LSTM with 100 hidden layers, activation of ReLU, input shape. Okay, input shape will take first number of time window, then the number of variables. Okay, then after that we will add one dense layer. Okay, which will be the uh, output layer. So finally we can compile the method with Adam optimizer and loss function of mean square error. Okay, so after doing all this, compiling the method, now our model is ready. We can run the model for fitting into data. So you can say model dot fit xtrain ytrain epochs of 10. So as you can see that it performed well till uh, uh, epoch 8 or 7. After that there is no much progress, so it means that model gets saturated till in epoch of 7. So it means like only 7 or 8 epoch will be uh, enough for this model, but for the safety you can put it as 10 or 20 to see if there is any improvement or no. So after feeding this into the data set, then we can predict for our test data x test. Then I have used r squared and mean square error for getting the accuracy measure of the model. As you can see that r square is 0.96, which is a very good uh, value for this, and mean square error is 0.008, which is a normalized mean square error. It is not the actual mean square error because we already normalize the data set into mean and max. Okay, so if we want to get the actual mean square error, we can do a reverse normalization, which will give us the actual values, and then we can find the actual mean square error. So this is a scattered plot of y rate and y test. As you can see that the data has totally fitted in a diagonal line. It is not spread it much uh, a lot around the line, but it is very close to the line, which supports this r squared value, right? That we got 0.96. Okay, so this is for y parade and y test, and we have plotted for observed and predicted. The blue lines shows the observed value, and the orange line shows the predicted value. So that forecasting was for multi-dimensional data set. As you uh, were watching, it was for 7-dimensional data set, but let's see how it will perform for only one dimensional data set. So here I have okay, so this is for attention. Here I have used only forecasting for one dimensional data set. Here I'm getting only the second column. As you can see, the second column only, and all the rows for the second column. Okay, this will be your data. Then after that I'm reconstructing the data. Okay, label will be 0 because I'm already defining it here. The data is only in one dimension. So after reconstructing again, you can see that here it is only one dimension with 100 time window with 9889. uh, for it is for testing, not for training. Okay, the test shape. So again you are putting that the same model, again fitting with 10 epochs, and you can see that the result is 0.95, which is close to 0.96, but still it is a bit lesser than multi-dimensional. Okay, so and also as you can see in multidimensional, the model became saturated in only seven epochs. Okay, but here it got saturated in 10 epochs. Okay, so it means like if you have a multi-dimensional data set, your model will perform well, and it will be easier for model to find that pattern of the data set. Okay, so that was for one dimensional. And then, so as you can see, like why we are using attention mechanism, as you can see here, after this value 0.014, there is no improvement. I have tested this model with more than 10 epochs also, but there is no improvement. So we need something more to improve this data, okay, to get more accuracy. So that is when attention mechanism comes into the picture. So I have used attention mechanism for further improving the data. For attention mechanism, after declaring the LSTM, we have to put this many seven layers, okay, between the LSTM and the final output layers. The first one will be dense, second flatten, activation, repeat vector, permute, multiply, and lambda. So after putting these seven layers, then you can put your dense layer, which will be your output layer. Then we can compile it with a loss of MSC and optimizer of Adam or any other optimizer which you prefer. Okay, so I have fitted this model, but it will take more epochs, more time to fit or to reach to its saturation. I have used 20 epochs, but you can use more than 20 epochs, as it has that potential to improve its performance. As you can see, from 0.014 it reached to 0.0013, then after that it reached to 0.012. As if we run this for more than 20 parts, it may increase its performance. It has that potential. That is why we are adding this attention mechanism. So i have I have predicted for excess, and then this is the result for 0.965. And not to forget that we have used only one dimensional data set for attention mechanism, which gave us 0.965, which is at least zero point zero 0.01 unit more than this r squared for one dimensional data without attention mechanism. So guys, this was about time series forecasting using LSTM and attention mechanism. I hope you enjoyed the video and learned something new. If it was useful for you, please do like the video and subscribe to my channel. I will upload more videos like this for time series forecasting using LSTM and all other machine learning techniques. I hope you enjoy and stay safe. All the best. Thank you so much.